All right, so last time we looked at our first very basic computational model, which was a finite state automaton. And here's an example. Remember that it's represented by this series of states along with state transitions. And it's got all of these, within these states, it can be an accepting state, which is represented by the double circle here, or a rejecting state, which is just a regular old circle. Let me make sure the audio is working. Good. All right, remember we are on YouTube, so if you have any comments, go ahead and post there. Otherwise, now we started an exercise last time. I want to go ahead and step back a little bit and talk a little bit more formally about this. So an FSA, or finite state automaton, defines a language. Remember, languages are subsets of finite binary strings. So it defines a language as follows. On an input x, which is a string, so sigma star, right? There we go. On input x, it transitions from the initial state to other states, depending on each bit, right? Bit by bit by bit. So it's read once, right? Read once and read only, right? It doesn't have any memory that it can work with. So obviously there is one limitation immediately that makes it different from a traditional idea of a computer. It has no memory that can store anything other than the input itself. And it can only read it once. It can't go back and say, okay, well, what was the third bit, right? So it's not going to be able to make such computations as this bit over here at the beginning, does it match this bit over here at the end? You're not going to be able to do things like that, and we'll be more formal about this here in a second. Once fully read, if the machine ends in an accept state, then it accepts x, right? If in a reject state, it rejects, right? As is straightforward, right? So that we say that an automaton A, right, decides a language L if for all inputs x, it accepts if and only if x is in the language. Right? Now, by exclusion there, if and only if, it accepts if and only if x is in the language, then that means that it rejects if and only if x is not in the language. And I don't need to write that again because that's by exclusion. Right? So there are some languages clearly that are that there is a finite state automaton for. For example, the one that we originally started out with right here. What did we come up with? That it ended with a 0, 1. Okay. This one is a little bit more complicated, but I don't think that it decides any, or that it defines or decides anything special. So what I wanted to do now is I wanted to come up with a couple of languages, and then we're going to design a machine for it, showing that that it's decidable by this very, very simple finite state automaton computational model. For example, let's go ahead and define the following language. It's going to be all x such that x is a string implicitly. That's our universe of discourse here. So we'll always just be talking about strings here. Such that x is a binary representation of an even number. Right? So can we determine whether or not an input is even or odd? Right? By exclusion, odd, because then that would be in the complement language, right? So give me some examples here. What about 0, 0, 1? Right? That represents what? 1. Just like 1 represents 1, or 0, 1, and 1. So all of these we would end up rejecting, right? What else could we reject? 1, 1, 1 is what? 7, so we would end up rejecting that as well. So what does it mean for something to be a representation of an even number in binary? Like 2, what is 2? 1, 0, right? 2, you would accept it. What's another value here? What about 1, 0, 0? What is that? 4. 1, 1, 0? What is that? 6, right? Dot, dot, dot. So what's the pattern here? That x is a representation of an even number if and only if what? It ends in 0, right? Good. So let's design a machine that accepts only if the last bit in the input is 0. I need an initial state here, so I'll go ahead and create this initial state. Right? Q naught. You don't even have to really label the states. But there's my initial state. So what about the empty string? Should I make this into an accepting state immediately? Probably not. Right? That doesn't. It's not a binary representation of an even number. It's not a binary representation of an odd number either. But choose one or the other. It doesn't matter. Throw it into the complement language if you want to. So if it immediately ends with a 0, right? Then I should accept it, right? Zero. Why? Because 0 is even. So if the last, if I'm currently in an accepting state and I got here by witnessing it ends in a 0, but it doesn't end anymore, right? Suppose that I see another 0. Where should I go? Itself. Just stay there. There we go. 0. But if I see a 1, and that happens to be the last bit, then I should reject, right? So let's go ahead and go back over here. 1. Now, have I defined all possible transitions here? Nope. What if I'm in this state here, and I see a 1? So 1, 1, 1, 1, 1, or 1, 1, 1, 7, right? I would want to stay in that rejecting state. So let's go ahead and put that here. And that's going to be 1. There. That is a finite state automaton that decides this language up here. If you want to, you can give it a name, L even. Right? So the language of all binary strings, finite binary strings, that represent an even integer is decidable by a simple finite state automaton. You don't need extra memory, right? You don't need to reread the input. You can just read it once. In fact, if this was a real computer program, all you'd have to do is look at the last bit and you're done. Right? You don't even need to read all the bits up to that point. So simple languages can be decided by simple computational models. Let's look at something else. Let's look at what's called the parity. Right? You might have seen parity bits before. Parity, that if you've got this binary string, count up the number of 1s. And if it's even, then your parity is 0. If it's odd, then your parity is 1. Right? So all x such that the parity of x is even. For example, 0, 1, 1, 0. Right? This is even. Why? Because there are 2 1s. 0, 1, 0, 1, 1. This is odd. Why? Because there are 3 1s. What about 0, 0, 0? Is that even or odd? The number of 1s in that is 0, and therefore it is even. What about that empty string? How many 1s are in that? Same. 0, so therefore it is even. Now, the way that I stated that was count up the number of 1s, and then if it's even, accept it. If it's odd, reject it. But can we count with a finite state automaton? We tried last time, and we couldn't really figure out how to do it. In fact, you can't. Right? So, just because I stated it as count up the number of 1s, is there a simpler way? So match each one to another one. So all I need to do is keep a flag value. How many ones have I seen so far? Even. Oh, I see another 1. 1. I see another 1, and I'm matching ones now, right? 1 matches with 1. That cancels out, and I'm back to even. See another 1. Okay, now now the state is odd again. See another 1. Now it's even again, right? I don't have to count up the number of ones. All I have to do is keep track of the one previous to it. Right? So again, let's go ahead and create a 2-state finite state automaton here. This first one will be my initial state. Right. There we go. And initially, on an empty string, I'm going to accept that. Right. Why? Because there are an even number of ones. There's 0 ones there. Okay. Now, if I see a 1, I will go over to this odd state. I'll even name them even and odd here. Right. If I see a 0, right, and I'm already even or I'm already odd, then what should I do? Just stay where you are. But if you're odd and you see one more 1, then you should transition over here. 1. So it looks very similar to what we just did here. It's just slightly different. Right? So yet again, with a 2-state finite state automaton, I can decide this language right here. It's a little bit more substantial now, right? So there are lots of things that you can actually, lots of useful things that you can come up with a finite state automaton, a regular expression for, and solve those things. Here's one that you can't. Now this is a simplified version of what we tried last time. What I'm going to do is I'm going to create a language here, 0 to the n, 1 to the n, such that n is an integer here. Okay. So for example, the empty string 0 1 0 0 1 1 0 0 0 1 1 1, right? These are all strings that are in the language, right? If you've got any other string that is not an equal number of zeros followed by a certain number of zeros followed by an equal number of ones, okay? That's what this syntax is here, or this notation is, right? This is n zeros / n ones, okay? So for example, 0 1 0 1, that is not in the language if I define this to be L. 1 1 0 0 is not in the language, right? Because it doesn't start with zeros, right? It has an equal number of zeros and ones, but it doesn't start with all the zeros and then have all the ones, okay? This seems like it should require some counting. Count up the number of zeros, count up the number of ones, and if you encounter any zeros within those ones, if you encounter any ones within those zeros, then reject that. Otherwise, if n is equal to n, you're good to go. Accept it. Right? Is there a way that we could possibly come up with a finite state automaton to do this? Yeah.
So if we have to have all the zeros in front, we could split them in half. We're either in the 0 section or in the 1 section.
Okay, so as long as we see a 0, we're in the 0 section.
And we just got to count the parity to see if the parity is 0 too.
Yeah. As long as we're in the ones, we stay in the 1 section. The second that I see a 1, I jump over here. The second I see a 0, though, I go to a reject.
Yeah.
Okay. How many times? How do I have an assurance that if I did this 5 times, then I jumped over here that I would do this 4 times? So once I go up, there are 5 zeros, 5 0 0 0 0 0. There's 1 1. Right? Now I need 4 more ones. 1 2 3 4 5. What if there are a lot more than there? Then I need to know how many there were to begin with. So unfortunately, you could prove using what's called the pumping lemma that there is no finite state automaton that decides this. And it's basically kind of like that idea that you have this finite state automaton where you can have loops, but if you have a loop, then that means that you've got some repetition, right? You can repeat this string as many times as you want. And then on the endpoints, there are some things. But there's no way that you can repeat this string here, 1, 0, 1, and then like say, you've got a bunch of ones over here, and then a bunch of zeros and ones in between this thing. If it's a regular language, then this means that this could be repeated, and you end up with a bunch of interleaved zeros and ones. That's the high-level idea. Again, this is not a finite state automaton, or this is not a computational course. This is just an introduction to computation. But look up the pumping lemma. The pumping lemma allows you to define a property such that if this language has that property, you can pump it and then show that it's not regular, that there's no such finite state automaton that decides this language. However, if I give you a little bit more computation power, 0n, 1n, such that n is z. If I give you a little bit more computational power, you can actually decide this language. What's that little bit more computational power? It's a little bit of memory. Right? It's a very specific piece of memory. A stack. Now you can use the stack to remember how many zeros you had. Right? Here's the idea. You push zeros until you see a 1. Right? So if you push 0, 0, 0, 0. Right? Okay? And then what you do is you go into a different mode. Right? Mode 2. You pop zeros, matching each one. Or, yeah, matching each one. So if I've got 1, 1, 1, 1, right, and I pop, 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 then I end up with an empty stack, and I accept. If I don't have an empty stack, or if I have more ones than I had zeros in this stack, or if I'm in this mode and I start seeing a bunch of zeros again, I saw a bunch of zeros, then a bunch of ones, and then a 0 again, I reject. Right? So if I gave you this little bit more computational power with a stack, it turns out that you can do provably more computation. What could I give you even beyond that? Remember back to assignment 1. What was there? There was an exercise in there about computational power. And you simulated one stack, or you simulated one stack with one queue. But could you do it the other way around? Could you simulate a queue with one stack? I didn't show you that you couldn't do it, but you can't do it. Right? You need at least 2 stacks, and with 2 stacks, you can simulate a queue, and it turns out that with a queue, you can do anything that any programming language can. Right? So, finite state automaton, a little bit of power. Right? If I add a stack, these are called push-down automatons because you're pushing down into the stack, right? Then a little bit more. And if I add a queue, wow, you can do anything that you want. Right? All you need is one queue. Now, it's an unbounded queue, so you're not limited by any memory or anything like that, but that's the idea. Right? So, a finite state automaton is extremely limited. I had thought about doing an exercise here where we actually program this stuff, and I don't know how useful that is because it's not really finite state automatons, it's a full programming language here. But just really quickly here, what would it look like if I did program, say, the parity? Right, here's my input. You're not allowed to use any additional memory. You're not allowed to use any additional data structures. All you're allowed to use is what? One variable, right? Even initially it is true, right? So for each bit in the input, if that bit is equal to 1, then what do? I flip even to odd, odd to even, right? So this will end up being not even, right? So if it was even before, if it was true before, it'll become false. If it's false before, it'll become true. Right? And all I need to do is output even. Right? Try it. Right? Print parity of 0, 1, 1, 0. What should that output? Demo. Oops, oh, sorry. That was loud. All right. Oops. Output even. Return even. Sorry. I am thinking pseudocode here. True. All right. What about that? Is it even or odd? It is false. So false. Okay. And then if you want, we want to, again, I don't know if you want to do this or not, but what about that other language, right? So def zeros then ones, right? Input. How would you go about programming this? Again, you cannot use any, you can only read it once. So you can use a for loop to, like we did up here, but you can't use, you know, all right, do it over again and like go back and forth. Counting, you can't do, I mean, you can't do that with a stack necessarily, but you can push stuff into a stack. So let me go ahead and give you a stack now. Right? S is equal to, now in Python, what is a stack? It's just a list. Right? So what would this look like? It's kind of fun to do this kind of stuff. It's because it's program this, but you know, give yourself a handicap. You're not allowed to use a dynamic data structure, or you're not allowed to, you know, use a for loop or something like that, right? Do it recursively. Force yourself to use recursion or something like that, right? So I will go ahead and create a mode here, the 0 mode, right? And for each input, x in the input, right? If my mode is 0, that means I'm reading zeros, right? So 0, 0, 0, 0, 0, 0, 0. What do I do? And the input is a 0. Then what should I do? I'm reading zeros. I will push a 0. So in Python, we don't push, we append, right? A 0. There we go. Otherwise, if my mode, or elif mode is ones. In other words, I'm no longer pushing zeros. Now I am popping ones, right? So what would that look like? And x is equal to 0. There we go. Then what should I do? So I am popping zeros, but then I see another 0. In other words, I saw a bunch of zeros, then a 1, or maybe a bunch of 1s because I'm doing this in a loop. But then I see another 0. Should I accept that or reject it? Reject. So I'll return false. Right? Else. What else do I do here? So this takes care of both situations where I see a 0. Otherwise, down here, you see a 1. Right? And you can do that explicitly if x is equal to 1. But that's the only other possibility here. So what I'll do is I will go into my 1 mode. I might already be in my 1 mode, right? But if I am and I see a 0, then I immediately reject. So now I'm in my 1 mode, right? And I'm reading 1s, I should pop a 0. But what if there are no more zeros to pop? So I pushed 4 zeros, popped 4 zeros for 4 1s, but then I have another 1. What should I do? Reject. Return false. There we go. Else, and then I don't need to do anything with it. And in Python, to pop, we do pop. Oops, sorry. I think there, S, and then pop. There we go. All right. When I'm done reading the input, bunch of zeros, bunch of 1s, all right? Then I got out of this loop. I never found a reason to reject it. So what should I do? True. Accept it. Now, I did write this beforehand, so let me go ahead and, actually, sorry, no, there's one more condition, right? So if S. So hopefully we understand what this is doing here, right? An empty list is true or false? False. So if it's not empty, right, then return false. If it is empty, if it is not empty here, right, then that means that you have remaining zeros. You pushed, say, 5 zeros, but you only matched 4 ones. So you've got this extra 0 down here. What should I do? Reject it. Else? Accept it. Okay? Now, I wrote a bunch of tests here because I did this just as a whim, right? And we all agree that these are, like, this is true, true, false, and then all the rest of these are false, right? That's what they should all be, right? So let's go ahead and call this for each one of these. I called it, what did I call it up here? Zeros, then ones. There we go. And let's run it again, make sure that we got everything. Oops. I saved it, right? Oh, you're right. I didn't, that's a bad test. It's a silent test. Else, printf, or print success. There we go. That's going to print out a whole bunch of successes. Yay. I did it. Okay. So the takeaway here is, even though I'm using this very powerful Python programming language that can compute anything that's actually computable, by hamstringing myself, tying one hand behind my back or something like that, and only allowing you to read the input once, but giving you the power of a stack, you can still compute this. Right? Just like finite state automatons. You have no memory. You have a read once only input. Well, if you give it a little bit more power, a stack, then you can provably decide more languages. If I give you a queue, you can decide any language that you could devise over here in Python. A queue and a finite bunch of states turns out to be just as powerful as any computer. Not as efficient, but just as powerful as in terms of the number of languages that you can decide. So what is this thing here where we're given a queue? It's called a Turing machine. All right, let's see. You could use a queue to simulate a stack, of course. Yes, the question online. Yes, the other day I said that you were unable to count in FSAs. That's true. You're technically not really able to count, like go up for I being 1, 2, 3, 4. You're not able to do that, I believe, with a stack, but you can do it with a queue. All you have to do is think about the really low-level kind of details that you want to add one. Okay, well, that's you can reuse the queue just like your trick did, the trick that you used in homework 1, which is for a queue to simulate a stack. All you have to do is take everything and put it back to the end, put it back to the end, put it back to the end, and then you can get access to any arbitrary element that you want. Well, if you have access to any arbitrary element that you want, you can count in binary, right? And you have carry through. It's just really complicated to do it because you need a very low-level kind of idea of how to do it. So, what if I gave you a queue? Well, that's basically giving you the power of what's called a Turing machine. There we go. There. Okay. Ah, it's not formatting correctly. There we go. Fine. Oh, there. Okay, there we go. So a Turing machine is a little bit more power, right? It still has a finite set of states. Any computer will have a finite set of states, by the way, too. All you have to do is freeze the computer, look at the entire memory of the computer, which can be very large, but there are only a finite number of states that it can have. It's huge, but it's still but it's still finite. There aren't an infinite number of states with a finite computer, right? Sigma is an input alphabet, and now we're adding another alphabet here, an output alphabet. Okay. Now, typically, both of these will be the same alphabets. And then there's this transition function. You have the current state. You are looking at the 1 bit of the input at a time. You are looking at 1 bit of the output. And then you are making a decision on which state to go to next, writing to the output, and then moving either left or right on these on the input and output. Right? So you also have an initial state, and you have the single accept state and the single reject state. Okay. So to understand this, let's go ahead and just visualize it. And where's my Turing machine? There it is. So here's what you should be looking at it as. Right? We've got this input tape. It's read-only. And I'll annotate all this. This is a read-only input tape. Each one of these things is a bit. Right? This is known as the tape head. And you can kind of understand why they called it tape heads back in the 40s, 50s, whatever it was when Turing came up with this. Why? They were using tape. Exactly. Right? So this is a tape head, and this is the output tape head. And this is you could also look at this as a work tape, because whereas the input tape is a read only, this is a read write. So you can read from this and you can write to it. Initially, it's going to be all blank. Each one of these special symbols right here, this is a blank, unwritten bit. Okay. So you can either write zeros, ones, or leave it blank. You could overwrite it so that it's a 0 becomes a 1 becomes a 0, or you could just erase it entirely, and then you could make them into these blank values here. So you can look at this finite state control here and view it as one of these finite state automatons that we made. But you've got more complex transitions now, because you are looking at the input, 1 bit of the input, you are looking at 1 bit of the output or the transition or the work tape, and then you're looking at the current state and you're moving to a different state, possibly moving this tape head to the left or to the right, possibly moving this tape head to the left or to the right, and then you're transitioning a function. You might also be writing this. So, reading this, writing this one here. So you could say, write a 0 here, or write a 1 here, or whatever it was before, leave it and don't do anything with it. But move this tape head. You could also leave it there. That's why you have this other transition function, right? This, don't do anything with it. So move left, right, or stay where you are. What is this work tape right here in a computer? Memory. Right? So what did I just give you? I gave you a bunch of memory to work with. And with memory, now you can count. Now you can remember. Now you can simulate a stack. All you have to do is take this and then rotate it, and you see how this is a stack. You can write something here, write something here, write something here. Now pop means that you are erasing it and then moving the tape head to the left. So this can simulate a stack. This can simulate a queue. How? Well, treat the entire thing like a queue. And then if you want to dequeue something, right, then erase this and move your tape head to the left. If you want to enqueue something, move everything down to make way for it and then insert it right here. So I give you the power of a stack, I give you the power of a queue, I give you the power of memory. Right? And it turns out that you can now decide that language that we had problems with earlier. How do you do it? There it is. There's the machine. All right, don't worry about the details here. You start in this state. The way that you read this is, if you read a 0 on the input, it doesn't matter what you're reading on the output. Go ahead and write this special symbol to the output. Basically what you're doing is you're filling this up with hashes. Right? And you do that over and over and over again for each 0 that you see. Moving the tape head in the input tape here, don't move it, but move the work tape right. Move the work tape and the input tape right, and keep doing this as you're reading a 0. It fills up with all these hashes. The first time that you see a 1, right, then go into this mode, and all you're doing now is overwriting these hashes with an empty symbol, moving it right because you're popping, or you're moving the input tape right, and then you're moving the output tape left because you're popping. Right? If your queue or your stack, is empty, right? At the end, this one right here is that initial one that I put there just so that you know when it's empty. Then accept it. On the other hand, there are all the 3 other conditions here. That if you see another 1 and it's not empty, then that means you have too many 1s and not enough 0s. Reject. If you see another 0 after you've seen after seeing a bunch of 0s, see a bunch of 1s, and then you see another 0, reject. If you have more 0s than you've had 1s, then also reject. Right? And also reject in these special conditions here that if you see no 0s at the beginning and you first see a 1, well then go ahead and immediately reject. If it's an empty string, just go ahead and immediately reject. I don't know if that's correct there or not. Let's see. So it's an empty input. It doesn't matter what the output is. Reject. I don't like that because according to that definition, you should actually accept. But that's all right. It doesn't matter. It's just a different language. This is a Turing machine. Now, what does it look like to actually write this down? If you want to, check out the book because I actually went to the pains of doing this. All of the transition states are not available here. There are many more transition states. I put them all into this big giant table. And I labeled the ones that I did not depict in this graph here as impossible because they were not states that you could ever reach out on any possible input. And so I put not applicable. About like 2/3 of them were not applicable. They were irrelevant. But the rest of them, that's the power of this Turing machine right here, right? That is going to decide this language that we were working with. It's kind of like writing in assembly code, but from a theoretical point of view, right? You're doing this transition state. And writing it out in a big giant table is what's called a Cayley table, right? For transitioning between, from operation to operation. Right? It's not all that interesting. Writing Turing machines is pain. It is even worse than writing assembly code, right? It's not something that you'd actually want to do, which is why we come up with pseudocode and the Church-Turing thesis. Right? So, I'll go ahead and give you this definition here. There we go. And I need to go back over here. There we go. A Turing machine decides a language L if and only if it halts on all inputs and accepts or rejects whether or not it's in the language. Now, there's an additional piece of the language here, right? A Turing machine, TM, only accepts or only decides a language if it halts on all inputs. We didn't have this problem before with a finite state automaton and a finite state push-down automaton, did we? Because I said the input, you read it once. When you get to the end, that's the end of the computation. But what about a Turing machine? If it's just as powerful as any programming language, what could you end up doing? While true, print hello. What is this? Let me put it down at the end here. What's going to happen? An infinite loop. Right? So, just as programs are susceptible to infinite loops, so are Turing machines. If a Turing machine gets caught in an infinite loop on any input, it does not decide any language. Right? So you have to have this additional requirement that if and only if it halts on all inputs and accepts or rejects whether or not it's in the language. If you write a bad Turing machine, If you, just like if you write a bad piece of code here, then true, right? Then it's not an algorithm. This is not a valid program, right? This is not a valid Turing machine implementation if you want to look at it like that. All right. Has anybody ever seen like basic code? No? All right, well, here's the best basic program ever. 10, print, hello, or whatever, hello. 20, go to 10. You've never seen that joke before? No? Okay, that's basic. Basic, you actually numbered your lines of code, and so you had to do it, you had to label every line of code, so that's why you always went in increments of 10, 20, 30, 40, because what if you had to go back and add a piece of code between these two lines, right? You need 15. Okay, well, if it all fills up, then basically you have to go through and renumber every single thing, right? It's basic programming language. Don't do that. Anyway, that was used on a nobody's ever seen Look Around You? It was a British show. No, it was a parody of like educational, elementary educational films. Check it out sometime, right? It's Look Around You, right? All right, anyway, dry British humor. So the question here is, are Turing machines equal to computers, which are equal to, of course, our concept of what are known as algorithms, right? Can Turing machines compute or solve? So what we're going to do is, remember that we started out with, can algorithms solve any problem, right? We're going to now reformulate this to say, can Turing machines decide any language, right? So that first one, are Turing machines equivalent to computers which are equivalent to algorithms? That's known as the Church-Turing thesis. So the Church-Turing thesis is that Turing machines are equal to algorithms, which implicitly are equal to computers, right? So I did not label this as a theorem. What's a theorem? Theorem is a mathematical statement that is either true or false. Is this a mathematical statement, though? Turing machines are algorithms, and algorithms are computers. Turing machines are a mathematical definition. Right? You have a very rigorous mathematical definition as laid out right here. Right? They have a Cayley table. They have, they have a finite representation, et cetera, et cetera, et cetera. But what about an algorithm? What is the definition of an algorithm? That's a dictionary definition. Right? So why is it a thesis? It's because it's not a true or false statement. A thesis is simply just an assertion that we stand up and we say, all right, there's this model of computation called a Turing machine, and we are going to accept that as our idea, our mathematical idea of what it means for an algorithm, right? And that's why it's a thesis. Now, why is it the Church-Turing thesis? Because Church came up with an alternative computational model called lambda calculus. And you can now lambda calculus is a mathematical definition. Turing machines are a mathematical definition. You can use mathematics to show that this definition is equivalent to this definition and vice versa. So, wow, these two things agree. We're probably on to something here. Right? This is probably what we do mean by algorithms. You can accept it or you can reject that, right? Just like a Turing machine can accept or reject. It's a thesis. It's not a theorem. It's not something that you can prove true. It's not something you can prove false. It's just that, all right, come up with your own computational model. You think you can do better, right? Come up with your own computational model and prove that it's either equivalent to one of these models, in which case, great, you came up with a third way of expressing the same thing, and you now agree with the Church-Turing thesis, or you come up with some weird model where you just give it an infinite amount of power or something like that, and then nobody will listen to you, right? Because I think that the model of computation is, I can't think of any absurd model, I guess. An oracle sitting in methane bath, getting high and coming up with weird answers or whatever. Anyway, it's the Church-Turing thesis, and it's not the theorem. What about that second part? Can algorithms solve any problem? In other words, now we have a mathematical way of expressing that. Can Turing machines decide any language? What do you think the answer is now? So answer, no. In other words, you can come up with problems, right? Actual, real, practical problems, such that no Turing machine decides that language. It fails for at least one input that you can give it. It might fail for many, many other inputs, but it fails on at least one input. In other words, it gets caught in an infinite loop, or it cannot decide that language. This all goes all the way back again to self-reference, and we're going to look at the proof next time, but it goes back to self-reference. This sentence is a lie. Is it a lie? If it is, then it's lying, and therefore, or this sentence is false. Let's just say that. Is the sentence false? Well, if it's false, then it's true. If the sentence is true, the sentence says that it's false, so therefore it's false. It's a contradiction. And that's how we're going to prove that there are languages that do not have any Turing machine that decides them. I'm going to show you two proofs next time. One's going to be a non-constructive proof using Cantor's diagonalization. Have you seen that before? No? So there are an infinite number of integers, right? There are an infinite number of real numbers. So are all infinities created equal? Nope. I can show that there are actually infinitely more real numbers than there are integers. One of them is countable and one of them is uncountable. Languages are uncountable. Turing machines are countable. And so I'll just use Cantor's diagonalization to show you that there are indeed languages for which there is no Turing machine that decides them. It's Cantor's diagonalization. And then I'll show you one for an actual practical problem called the halting problem, which would be very, very nice to have. If you could give a program to a compiler, and the compiler would say, wait a second, you're going to get stuck in an infinite loop on this particular input, right? That would be very, very useful. Oh, thank you for pointing that out. I think I'll go out and rewrite that code, right? What we can show is that there's no such algorithm, there's no such compiler that can do that on all possible programs. Now there are some programs, of course, that can simulate simulate it and say, oh, you got stuck in a loop. I can detect that loop, that you're obviously in a loop on that particular input, but it can't look at all infinite inputs and say, whoa, that one there, several billion down, that one's going to cause you problems, right? There's no such algorithm to do that. There's no such program. Right? Should acceptable problems for consideration be self-refutable, like if X, then not X? I'm not sure what that means. The proof that we're going to be looking at is simply is actually completely acceptable because you do it all the time. The way that I'm going to show it to you on Friday is you feed a program into another program. That's not weird, right? What is an operating system? An operating system is a program that runs other programs, right? What is an emulator? A program that runs a program that runs a program. What is a virtual machine? It's a program that runs an operating system that runs programs, that runs emulators, that runs programs. Now, go even higher. What is Docker virtualization? Oh no, it's containerization, containers, right? You can have a whole bunch of containerization, then you run a virtual machine on top of that. Container, virtual machine, container, virtual machine, right? So you can have programs running programs, running programs, running programs. That's all hardware is. Hardware is just running software. Hardware is a program. Software is a program. It just runs the program. So we're going to have a sentence that refers to itself, a program that refers to itself. Sounds like recursion to me, right? Exactly. The recursion is at the lowest level, where you've got a function, running itself. Right? And if you do that, then it opens you up to these weird things where you can't solve this problem. Right? All right. See you next time.